continuing, let's revise briefly and then we are going to finish the lecture. Basically, just to revise the different topics that we have looked at so far. So we are in the supervised learning domain. What we have done so far is decision trees, naive Bayes, KNN. And remember, supervised learning means that the the data set that we have, it consists of the input and the desired output. And for these three algorithms, decision trees, naive Bayes, and KNN, the desired Y, the output has discrete labels. For example, in decision tree, we looked at the case where we wanted to classify the data into different classes. For example, positive class, negative class, things like that. Similarly, naive Bayes and KNN also, we had discrete set of labels, either binary labels or multiple labels. And so whenever we have discrete labels, we call that problem classification. And when we have continuous, when y is a continuous number, it can be any real value, then we have a regression problem. So the algorithm that we studied last week, linear regression, it falls in the regression category where my y is continuous. And you also did the lab in linear regression. And by the way, the lab is very important because that forms the basis of deep learning that we are going to study from maybe next week or after the OHT 1. And it's a very important topic. Please uh, uh, focus, or I mean, do the lab really well. It's not much to do. A lot of code is there. You have to fill in few lines of code, but the important thing is that you understand the lab, do it yourself, and yeah, try to understand the lab. That will also help you in understanding the lectures. So again, recap that we start by defining the hypothesis. This is my linear hypothesis in the case when the uh, input dimension is 1. So my feature is just the size of the house. And if I have multiple features, then the hypothesis changes accordingly. For example, this is my hypothesis now, corresponding to n different features. So for example, I have 4 features here: x sub 1, x sub 2, x sub 3, x sub 4. And to revise the notation, the subscript is used to denote the features and the superscript to denote the examples number. For example, if I write xij, it means I'm looking at, or I want the value of the jth feature of the ith example. So this is the first example, second example, third example, fourth example, and similarly the first feature, second feature, third, fourth, and so on. And since it is a regression problem, so y belongs to a real number, any continuous value I can have here. So this is the hypothesis, and remember we also talked about the vector notation. So this theta bold is denoted, it is a vector which is formed by concatenating all values, all parameters. And similarly for x as well, so this is also bold. This is a vector in which I concatenate all the features of the input. Uh, xn, and this one is a bias term. Is there for the bias term. Basically, this is the bias parameter, and the reason is that the hypothesis has this parameter theta 0, which is being multiplied by 1. Therefore, when you write the hypothesis in the form of a vector, then you need to append your feature vector by this 1, just to make this vector multiplication equivalent to the value here that we have. So this gives us theta transpose x. So this is my hypothesis, and the objective is to check. This is the hypothesis, these are the parameters, and this is my cost function, and the cost function is squared cost function or squared error loss. Uh, the objective is to minimize the cost function j with respect to these parameters. So I want to find such a parameters theta 0 to theta n which are going to minimize my objective function. Basically, whatever prediction I am making using the parameters minus the ground truth value, taking the square root and summing over all values or all errors of or training example errors, it will give me the total cost. I want to minimize that. And the way we did was, the way we tried to minimize this error was using the gradient descent approach. And just briefly, this is what we did in case of 1D. This, let's say, given 1D, I just have feature 1, 3 parameter 1, and this is my cost function. I'm going to start from some random location, and based on the gradient, I'm going to decide whether I have to increase the value of theta or decrease the value of theta. So for example, here the gradient is negative or the slope is negative. I will therefore increase the value of theta, and slowly I'm going to reach the optimum value where the cost is minimum. Here the slope is 0, and that is why I will stop here. So this is the basic gradient descent approach, and this is what I am doing. I will repeat this statement, and so this is theta j means if I have let's say if n is 4, for example, and 4 means that I have 4 features, so x1, x2, x3, x4. If n is 4, then my theta would be theta 0, theta 1, theta 2, theta 3, theta 4. So I have to update these 5 parameters in each iteration. So this is, just I'm writing j, but j goes from 0 to n. Old value of j, the learning rate, and then the slope, the derivative, the gradient, which is going to tell me whether to increase or decrease the value of theta. So this is the gradient descent approach. That with the help of with the help of that, we are going to find the value of theta. For the case when n is 1, which means that it is a single variable, I will have to update only 2 parameters, theta 0 and theta 1. And these are the equations. The value of the derivative is this. Basically, if you remember, this was the cost function. And 1 divided by 2m. So rate of change of theta with respect to, for example, theta 0 is equal to 2 times 2m. Then you have the summation. Okay, and finally you have to compute derivative of this part again. And since y is a constant as far as theta is concerned, we need to only compute the derivative of this prediction, and this is equal to theta 0 plus theta 1x if I have just one variable. And so for theta 0, I will multiply by 1, so that is why I have just 1 here. For the x, I need, and for theta 1, I will have xi over here, and that is why I have xi here. This is the case for when n is 1. For n greater than 1, it's exactly similar. The thing is that this time I will have to update for j0 to n. So depending on how many parameters, how many feature points you have, this will be updated that many times. For example, theta 0, theta 1, theta 2, and you can easily see here the value with which I am going to multiply. So theta sub 0 means it is the bias term, it is always 1. So you can actually write 1 also. And in other cases, you will have the corresponding feature for the ith example. Okay, if you are doing it for theta 2, then the second feature of the ith example. So basically, then this I goes from 1 to m. So you have to do that for all the examples. We also looked at gradient descent. We also had looked at the feature scaling, and the objective is to scale the features to and normalize them so that each feature has same similar effect on the gradient descent process. Okay, then we also looked at the way to choose the learning rate. Okay, and basically we are still in doing the revision, so I'm skipping some of the slides. Finally, we looked at the batch gradient descent and stochastic gradient descent. Batch gradient descent is what we have been doing. This is batch gradient descent that we have to repeat this for at each iteration. So at each iteration, what we are doing, let's say if this repeat is for 10, if we say repeat 10 times, 10x times. So this part will be repeated 10 times. And as a result, each parameter, each theta will be updated 10 times, right? And for each update, I have to compute this part where I am summing over all values or all examples. As we discussed last time, this creates problem because if you have a lot of examples, for example, if m is 100 or million, you have to do this summation 1 million times before you get an update, and that you will have to do for each iteration. So this takes a lot of time to convert. Take out this summation from here and move it over here outside. So this results in the stochastic gradient descent. As you can see, we have the for loop here instead of the summation here. Okay, so this should be actually m because we have m examples. Please make this correction. I will also upload on the correct version, but you should know that this is m. So for I is equal to 1 to m, I have to repeat this part, this equation. What this says is if I am repeating this outer loop for 10 times and I have 100 examples, then in total I will be doing 10 times 100 times 10 updates, so 1000 updates for each parameter. So this will result in faster convergence for the gradient descent algorithm. So that is why this is favored. Actually, we will see later on that we also have a mini batch. Mini batch is that in between the stochastic gradient descent and batch gradient descent, where we do not update for each example, but we do it for maybe 10 examples at a time. And if you have 100 examples, so we will be doing the update after each 10th example by summing the values of the gradient of for 10 examples and then update and then move on to the next example. But that we will cover later on. Right now, there are two types of gradient descent: batch gradient descent, where you have this summation where this is the gradient. In stochastic gradient descent, you compute the gradient for each example, update the theta parameter, go to the next example, compute gradient for that example, update theta, and so on. Okay, we're going to do that, the example for this case in a moment. Okay, so this was last week. Any question up till now before we move to the normal equation? By the way, we may have a quiz next in this class from the lecture that I just revised. So please pay attention. So any question? Okay. So the normal equation, what this is basically another way of optimizing or finding the theta parameters. Remember, in gradient descent, we do it iteratively. We start from some initial value of theta, and then depending on the gradient, we decide whether to increase theta or decrease theta, and we do that iteratively until we come to the optimal value where the slope is or the gradient is 0. And this is iterative approach. Another approach is called the normal equation, where we solve for theta analytically, which means we will get an equation, some equation where we put the value for in the equation and compute the value of theta in a single step. So let's do that, and let's see how can we do that. For example, this is my training data. What I'm going to do is to create a big matrix X which contains all my examples. And before doing that, remember we also need to add the bias term, because we are doing the vector using the vector we are going to compute the calculation. So we also need to add this bias term. Okay, bias term simply means that we append each feature, each example with a 1. Okay, and the reason is that, remember, theta is theta 0, theta 1 up till theta n, and similarly x is also 1, x1 to xn. So this one we have to add for all the training, for in this case 4 examples, so we have to append that to as an example. So let's create a big matrix. The first row would be this one. Take it for 1 2 1 0 4 5 1 45. Similarly, the second row 1 4 1 6 3 2 4 0, third row, and fourth row. Okay. So this is my matrix X, which is here. Similarly, I also do the same with my matrix with the prediction, the ground truth. Y, I create a vector, and so each element comes from the corresponding row. Now I have a vector of parameters also, theta 0 to theta n. If I multiply x, or this vector, with x by theta, so what should it give me? If I have the right theta, the right parameters, what should x multiplied by theta give me? Look, this is x, this part is x. If I multiply by theta, which means I multiply by this vector here, so this multiplication is matrix multiplication, so I have the first row multiplied by the column here. So this is the prediction, so I will get the prediction for the first example. Similarly, the second element would be the prediction for the second example, and so on. So ideally, when I multiply x with theta, it should give me what?
Hypothesis की वैल्यू जो हमारी देगा values.
It should give me this vector y. That is if theta is right, it should give me y, right? So now I have an equation. So x theta is equal to what? This is an equation, a linear equation with the unknown. This is the unknown. I can compute now theta by multiplying by inverse on both sides, x inverse y. This is going to give me identity. So I am left with the equation theta is x inverse y. And since x matrix is not square, I need to compute a pseudo inverse. So instead of simply this inverse, I'm going to compute pseudo inverse. And pseudo inverse is basically something like that. Or pseudo inverse is this part here. This whole is a pseudo inverse. So this is going to give me the theta in a single step. I just need to place these values in and compute the parameters. ठीक है, this is normal equation. And in Python, you can compute the inverse using this. NP is numpy. So you have the numpy has this package linear algebra dot p inverse is going to compute the inverse. So in order to compute theta, in the lab also you have this question. So you just need to do dot p inverse x times y is going to give you the theta. Okay, I mean, I think it's not x, you have to multiply with x transpose also. But anyway, so this is for the lab. So the next question is then, if we can get the parameter theta in just single step as we did here using normal equation, so why do we need to go through, or why did we study gradient descent and went through all that trouble when we can easily find this theta in a single step without any iteration and whatever we studied? Any
सर
guesses?
क्योंकि मैट्रिक्स इन्वर्स लेना बहुत हाईली कंप्यूटेशनल प्रोसेस है और ग्रेडियंट डिसेंट रिलेटिवली आसान है.
ठीक है, good. So as rightly said कि for shorter problems जब आपके पास इन जो data set बहुत छोटा है, inverse is no problem, you can easily compute that. And that is why in the lab also data set is not big, you can compute the inverse, it's not a big problem. But when the problem is large scale, and that is what usually is in machine learning, that your training data, your features are very large. In that case, computing inverse is not feasible. It takes a lot of time, and sometimes you also have instabilities in computing the inverse, and that is why for larger problems, large scale problem, we favor the gradient descent approach. And this slide simply lists some of the pros and cons of the gradient descent and normal equation. In gradient descent, one of the cons is that you need to choose the learning rate, where you have to basically do hidden trial to come up with a good learning rate. It needs many iteration. In case of normal equation, no need to choose alpha, don't need to iterate. So this is very good, so far. However, if your n is large or m is large, in that case, gradient descent will still work, but normal equation will be very slow. Okay? So that is why gradient descent is the approach that we take for large scale problems. This finishes the lecture, and we're going to do an example of linear regression. So before doing that, any question?
सर जो आप लार्ज स्केल और स्मॉल स्केल कह रहे हैं इसमें हमें कैसे पता चलेगा कौन सी लार्ज स्केल है कौन सी स्मॉल स्केल है?
अगर आपके पास डाटा ज़्यादा है तो लार्ज स्केल है, फीचर ज़्यादा हैं आपके, तो sometimes you have features, million features, 100, 200, 300, 400, in thousands features. Is the training setup data आपके पास ज़्यादा है, तो in that case it's a large scale problem.
सर फीचर्स या नंबर ऑफ रिकॉर्ड्स?
दोनों की हम बात कर रहे हैं कि क्योंकि दोनों का इफेक्ट आपका पड़ता है उसके ऊपर, इनवर्स की कंप्यूटेशन पे.
ओके सर.
Okay. So I have also uploaded this OHT1 sample. which contains a lot of, I mean, not a lot of, but some of the questions that you can expect in OHT1. Please do that. The solution is also there, but do the question yourself first and then look at the solution. What we're going to do today is to go through one of the question related to the regression problem. Okay. What's happening? Okay, so let's look at this problem here. Sorry. So the problem is to use stochastic gradient descent. Use stochastic gradient descent to find the optimal theta for linear regression using the data set X. This is your input X, this is your desired Y. So first let's see what is the data set. The data set is basically, since there are two features, so I have X1 and X2. And then I have the Y. So X, for example, looking at the first training data, which is 1, 1. The first feature is 1, the second feature is Y, and the ground truth value for that is -3. Similarly, 0, 1, -1.5, 1, 1, 0, and the last example is 8, 3, and the ground truth value is 30. So this is my training data, and I have to use stochastic gradient descent to find the parameters. And remember, parameters basically means I have to find theta 0, theta 1, theta 2. If I am doing using the vector notation, maybe I need to add the x0 term also, just for my ease of computation. So it will be 1, 1, 1 for all cases. Okay, this is just the bias term. Okay, so this is the training set. I have to find the updated parameters. Okay, let's read the question further. The hypothesis function for linear regression is this. So this is my hypothesis function x. Okay, so x basically means, if I'm talking about whatever example I'm talking about, if I is 1, then I'm talking about this part here. If I is 2, I'm talking about this one, I3 and I4. This is my hypothesis, but here the question says that assume zero bias. Assume zero bias means that you do not need to worry about the bias term, or you do not need to compute theta 0. Just assume theta 0 is 0, which means that we do not actually need to, I mean, even if it's there, we do not really care about them, because we are assuming it is 0. Okay? And x1 basically is this, x2 is this one, x sub 3 is this data, x sub 4 is this one here. Use linear regression loss function. So this is the loss function that I have to use, and the initial value for my parameter is theta 0, 0. Since I have only two parameters, I am not considering the bias, so theta 1 and theta 2. If the question did not mention that assume zero bias, then I would have specified the initial value as this, because I also need to specify the theta 0 key initial value ka hai. But right now we are assuming that theta 0 is 0. We are just ignoring that. That is why theta is theta 1 and theta 2. उसके बाद this is my loss function, and remember loss function is this is my loss function for the linear regression. ठीक है, this is my loss function, loss function or cost function, and I have to minimize this one. But since I am using stochastic gradient descent, which means that for each training example, I will use the gradient just for using just that example and not some overall values of the training examples or all values of I. Which basically means if I just look at one example, then my loss is simply this. Okay, just for that example, so loss at ith example, let's say, or let me write the superscript. So this is the loss for the ith example. So I will compute the gradient of this with respect to the theta and update my theta parameters and then move in that iteration. So the question is clear to all now, the loss function and everything. Okay, let's now move forward to the solution. How are we going to, or first let's write the gradient, the stochastic gradient descent algorithm. The stochastic gradient descent algorithm is like this. I have to repeat this part here for, I mean, till convergence, or I can even either specify that, okay, repeat for 10 times. In the question, I'm saying repeat only for 2 iterations. So repeat 2x times. And since it is gradient descent, it is stochastic gradient descent, so I have a loop here for I is equal to 1 to m, which in this case m is 4. So let me just write m4 here then. So for I goes from 1 to 4, and at each of for each example I need to update my parameter theta j using old value of theta j. Essentially here I will only have theta 1 and theta 2, so I can either use theta 1, theta 2, maybe I can use theta 1 and theta 2, or let me just write, just to make it generic, theta j. ठीक है, जहाँ भी let's also write here generic also, so that we are not specific to only this question. So repeat this, theta j, old value of theta j minus the learning rate, where I have specified in this case the learning rate is 0.1, and then here I have with respect to the theta j, and since j, we will have another loop here because j goes from 1 to n in the general case, or 0 to n, because I have to also update the bias term also. So this is the general algorithm for, this is general stochastic gradient descent algorithm. Stochastic gradient descent algorithm. Okay, and this has to be repeated again and again. So this once this one loop, or once this this bracket, this is finished for all m examples, we can also call that one epoch. So one epoch basically means that you have run this through the whole training data once. So this repeat is for 2 epochs, mean that you have to repeat, go through the whole training example 2 times and 3 times and so on. So the other thing is, if the question was batch gradient descent, in that case you would not have this loop here. Instead, this loop would be basically here. in the computation of the gradient, because in the computation of the gradient you would have the sum which will go over all examples. But since we are doing stochastic gradient descent, we have a situation like this. Okay, and let me also write the value for this gradient. So instead of writing this, let me write the exact value for the gradient. If you remember that this is equal to, or we can actually compute the gradient of this equation. So this is h of x minus y, and then again I have to compute the gradient of, because now in the first I have taken 2 here, so 2 times this, but 2 I already have 1 divided by 2, so that goes away. I'm left with h of x minus y, which is here, and again compute the derivative of h of x because y is constant as far as the parameters theta are concerned, and so h of x is given by theta transpose x. So I'm computing the derivative with respect to theta, so I will get x here, and not just x, but it will be the jth feature of the x. And let me also write xi here because I have to do the for each example. So this I goes from 1 to m, and at each, so how will I proceed? I will pick, when I come here, I will pick first example, repeat this part. So this will use the first example to compute the prediction, its ground truth value, multiply by the jth feature of the ith example, update j theta j for all, theta 0, theta 1 to theta n, and then go to the next example and repeat this procedure again and again. Okay. Now let's get back to the problem at hand. In this case, the situation is like this, that this goes up till 4. This goes from 1 instead of 0 because we are not considering the bias term. And this is also, or maybe we just don't need to write this also because there are just 2 parameters. So we can, instead of for loop, simply write theta 1 is equal to theta 1 minus alpha. Similarly for theta 2. Remember, इस question में we are not considering the bias term. So that is why it is not here. Okay, any question up till now? So this is what we are going to do. Pick the first example, first data point, compute these 2 values, update theta, move to the next example, again update, and so on. And that we have to do 2 times, so repeat 2x times because the question says so. And secondly, in order to compute this, this updated value, I also need to compute the prediction. So computing this prediction, actually we call that forward pass. So during the computation at each time step, we are going to first compute the forward path, which is going to give us the prediction, and this whole statement is called the backward path in order to compute the gradient, or this part is the backward path which computes the gradient, and using that we update the parameters. So let's actually now do that, starting from the first example.
एक्सक्यूज मी सर
जी
सर बैच ग्रेडियंट डिसेंट में हमें सारे ट्रेनिंग एग्जांपल्स के लिए सिर्फ एक दफ़ा फॉरवर्ड पास करने की ज़रूरत है और स्टोकेस्टिक में हम हर एग्जांपल के लिए हर दफ़ा करेंगे फॉरवर्ड पास
जी, हम लेकिन उसमें जब बैच ग्रेडियंट डिसेंट में आपने प्रिडिक्शन जब करेंगे तो वो तो हर एग्जांपल के लिए आपको फिर भी करनी पड़ेगी. दी डिफरेंस इज के उसमें आपने सब एग्जांपल्स की फॉरवर्ड पास इकट्ठा किया, बैकवर्ड पास इकट्ठा करके उसको सम करके अपडेट किया थीटा को. स्टोकेस्टिक में हर एक का आप सेपरेट करके अपडेट करेंगे। तो फॉरवर्ड पास तो दोनों केसेस में यू विल हैव टू डू दैट फॉर ईच एग्जांपल अगेन एंड अगेन। द डिफरेंस विल लाई कि आप उस फॉरवर्ड पास और बैकवर्ड पास के बाद फिर ग्रेडियंट किस तरह कंप्यूट करते हैं। इन स्टोकेस्टिक you will just use that example to compute the gradient update theta. In batch gradient descent आपने उस सब वैल्यूज का जो ग्रेडियंट आया उसको सम करके एवरेज कंप्यूट किया है, उस एवरेज की मदद से फिर आप थीटा को अपडेट करेंगे। ओके, तो लेट्स now start by the first. So at time or the first iteration t is 1. This is my data, the first example 1 5, and this is my y minus 3. So I also know that the theta initially is 0 0 क्योंकि it has been specified here. अगर यहाँ कोई और वैल्यू होती तो we would have used that. Now the next thing is to update theta 1 and theta 2. ठीक है, जैसे मैंने कहा कि in order to do that I also need to compute h of x. तो इसलिए let's do the forward pass first. So h of x is for this example, training example जो हमने consider की है, is equal to theta transpose x, which is equal to 0 0 times 1 5, which is equal to 0. ठीक है, so my prediction is 0. And now I can compute theta 1. Old value of theta 1 is 0 minus alpha is 0.1. My prediction is 0 minus the ground truth value is minus 3. ठीक है, and then the derivative में you have also this part x j I. So I have to look at the j's feature, in this case the first feature. So the first feature of the example, the first feature is this one 1. So I will multiply by 1. So this is going to give me minus 0.1 times 3 is equal to minus 0.3. Okay, now theta 2 will be equal to the old value minus 0.1. ठीक है, अब देखें जो हम साइमल्टेनियस अपडेट की बात करते हैं वो ये मतलब है कि नाउ आई हैव टू कंप्यूट दी प्रिडिक्शन. सो आई एम स्टिल यूजिंग 0 0, ऑल्दो थीटा 1 को हमने 0.3 कर दिया है, बट ये अभी करंट टाइम स्टेप पे हम यूज़ नहीं करेंगे. ठीक है, इसको नेक्स्ट टाइम स्टेप पे T2 पे यूज़ करेंगे, बट नॉट राइट नाउ. और T2 पे भी नहीं, जब अभी तो हम फिलहाल T1 तब ख़त्म होगा जब हम सब एग्जाम्पल से गुजर जाएंगे. तो व्हेन वी मूव टू द नेक्स्ट एग्जाम्पल then we will use these updated theta values, but for in current here the same prediction will be used, which is 0 minus ground truth is this and multiply by the second feature, which is 5 here. So this will result in minus 0.1 3 times 5 15 and 1.5 minus 1.5. ठीक है, तो अभी आपके जो थीटा वैल्यूज़ हैं आफ्टर द फर्स्ट एग्जांपल वो क्या हो गई हैं 0.3 and 1.5. Now next we go to pick the next example, which is this one 0 1 of the ground was minus 0.5 है. 0 1 y is minus 1.5. ठीक है, y यहाँ से हमने पिक किया है, दिस इज योर y. Okay, so again forward pass, which means now theta transpose is minus 0.3 minus 1.5, x is 0 1, so this is going to give me minus 1.5. ठीक है, तो this is my prediction for the current training example. Now since The ground truth value is also minus 0.5. My value is also, my prediction is also right. So when I compute the gradient, you will see that it will not result in any update क्योंकि आप सही predict कर रहे हैं, so theta need not change for the current example. So the current value for theta 1 is this one, minus 0.3 minus, my prediction is minus 1.5 minus, the true value is also minus 1.5, and I have to multiply by the first feature, which is 0. So this all goes to 0. So I'm still at 3. Similarly, we know that theta 2 will also remain same क्योंकि यह part आपका 0 ही है. Theta 2 will also remain minus 1.5. So after the second training example, theta will remain minus 0.3 and minus 1.5. So the question says do that for all training example twice. So this is the first iteration, और इसमें पहले आपकी वही वैल्यू आ गई, फिर सेकंड में वही रही, थर्ड एग्जांपल में देयर विल बी अ चेंज, फोर्थ एग्जांपल में देयर विल बी अ चेंज. So this is one epoch, you have gone through all the training example. In the next iteration आपने दोबारा इसको go through किया, you ended up here. The solution has still not converged, which means convergence कब होगी कि जब आप एक iteration में सारे training example से गुजरे and there is no update, just like here कि यहाँ आपका एक training example में कोई update नहीं हुआ था थीटा पे, but in the next training example you had an update, so you have not converged. So convergence तब होगी when there is no update and you go through all the training examples and still you do not get any update in your theta parameter. So that is where you will, I mean, in the true sense stop. But in exam I will tell you, okay, one iteration करना है, दो iteration करना है, because in exam it's difficult to go till convergence. Okay, so please do that remaining iterations, do that yourself by hand and see whether your answer matches the answer given here. और नहीं समझ आती तो discuss with me again, but you have to do that yourself. So also go through all different questions in this document. It contains sample questions that you can expect to see in your OHT1. Mostly, you know, from decision tree, naive Bayes, and linear regression, and the next topic that we are going to study now, logistic regression. So we take a break and we are going to come back or restart from at 3 o'clock. Or, I mean, and any question before we take a break from this example that we did here, this example here. Okay, so we take a break and then we come back.